the potential of AI ECG that shows potentially revolutionary capabilities, the potential to completely transform clinical practice and the clinical care pathway. And yet, for all this huge promise, there are real barriers that still remain that impede the wide adoption of these tools. So that motivates a lot of the work around explainable AI. That motivates a lot of my work as well. So these barriers are mostly associated, again, with the black box nature of many AI ECG models, lack of transparency or explainability, which makes them harder to assess and validate their outputs, the potential for bias or the lack of robustness, lack of human reasoning and common sense that we trust, the concern for high number of false positives, low specificity, too much false alarms, especially for endpoints of low prevalence. And all these characteristics may make these systems much harder to integrate in clinical workflows in a way that is trustworthy, in a way that empowers and augments the clinical intelligence. You know, expert criteria systems such as 12SL, you might call them as symbolic AI, as one form of artificial intelligence, but they are inherently interpretable. They are interpretable by design. So they have a lot of characteristics that very directly address all the weaknesses of black box DNNs. Their diagnosis is fully interpretable. It relies on meaningful ECG features, and criteria. They encode expert reasoning and guidelines very directly. That makes them more trustworthy, arguably, and more robust and generalizable. Their transparency and structure, in principle, allows clinicians to assess interpretation. You can point some limitations in how these characteristics are actually leveraged in practice today, but there's a lot of reassessment and reevaluation of these features in the context of TNNs that we can do. And finally, the criteria are inherently more specific, controlling a lot of false positives. So specificity is higher than 99.5% in many endpoints for 12SL interpretation. So a lot of these characteristics could be critical towards addressing all the limitations of black box DNNs and bringing them to practice, and towards deploying these AI ECG systems with much more trustworthiness. So, of course, we need to leverage AI and machine learning to improve ECG interpretation, but the black box paradigm leaves behind the interpretability, reasoning, potential specificity of these expert systems that are also already embedded in clinical workflows. So that motivates our work. We presented it for the first time last year. We leverage machine learning to develop and optimize criteria systems exactly like 12SL. So we use machine learning as the optimization process in a way that had never been done before for these criteria systems. But the criteria that come out of this machine learning process are fully interpretable and fully transparent, exactly like the criteria that exist in 12SL today. And they have built-in domain expertise, guidelines, and reasoning, in fact, built into the development process. That also goes into the feature engineering in a way that is very similar to what Dr. May described. So these machine learning methods can enhance criteria-based interpretation more efficiently than was ever possible, and provide a much more meaningful baseline to compare black box DNNs against. And that could represent a leap forward for criteria-based systems to use machine learning optimization at this scale, while also maintaining the crucial, potentially critical for how we leverage AI ECG, fully interpretable by design characteristics. So as a pilot application, we sought to improve left bundle branch block interpretation by 12SL. It is both very critical for diagnostic decisions, and it was an area that we saw that performance was lagging behind, and those criteria were not improved in a long time. So using that precision, this procedure, leveraging machine learning, in this case to indicate a false positive diagnosis by 12SL, and training directly on the cases that physicians actively removed the left bundle interpretation by 12SL, we identify criteria. So this is criteria that come out of the machine learning process. So presence of a non-monomorphic R wave laterally, short R wave peak time laterally, lack of QRST discordance, longer R waves in V1 to V3. So fully interpretable, meaningful criteria, meaningful to experts, again, extracted through data-driven machine learning methods in a way that had never been done before, and composed of many 12SL parameters. And there are around 600 of these parameters that come out of a MUSE system by default, and we have access to thousands more. And again, there's a lot of feature engineering that goes on as well. So because they are fully interpretable, you can see that they correspond pretty directly with standard guidelines for left bundle branch block interpretation. Certainly for the presence of monomorphic R wave laterally, longer R peak times laterally, QRST discordance. These are standard guidelines for interpretation of left bundle branch block that we can map onto the many different sets of guidelines that exist for this condition. And again, there was a back and forth of the machine learning optimization and injecting clinical knowledge and these guidelines into the development as well. But the longer R waves in V1 to V3 is something that you can't find in practically any guidelines. And we really struggled to understand it. At first, we thought it was a statistical error. It was a sign that bias can arise through this process as well. But in fact, consulting with experts, and some experts in this room probably understand this, it does make sense. A longer R wave in V1 to V3 indicates longer normal septal depolarization from left to right, and therefore it increases the chance of activation of the left bundle branch block, left bundle branch. So it points away from the left bundle branch block interpretation and towards IVCD or IVCB or left anterior fascicular block. There are other choices. So this is a strong predictor. It doesn't exist anywhere in the guidelines. Experts may know it. It's one of the patterns that they see, but it never actually made it in the guidelines. Of course, septal depolarization is the reciprocal pattern to the presence of Q waves laterally, which does exist in all guidelines. But it turns out that the data predict those patterns in V1 to V3 much more powerfully than what exists in the expert guidelines. So it's a potential demonstration of how data-driven criteria could be even deeper, more precise, more powerful for the specific target than guidelines, and allows us to access deeper patterns, but not only expressed in a black box performance, but also draw meaningful insights from them as well. We demonstrate that machine learning methods can improve ECG interpretation very efficiently, much more efficiently than ever before, without losing full interpretability and maintaining encoded reasoning and domain expertise and guidelines. It's a way that these criteria systems have never been benefited from this data-driven optimization at this scale ever before. Ian, legendary in the field, tells me we will never develop criteria in the same way we used to ever again. And we hope that this could be achieved for structural heart disease endpoint as well. These are endpoints that are beyond traditional interpretation, what has been traditionally the targets of 12SL. Many people say that these endpoints are the domain of magic black boxes, and it's beyond what humans can see. But there's a lot of literature that identifies a lot of structured patterns on this endpoint that hopefully we can see that structure on these endpoints as well, and we can leverage and draw insights in those applications as well. So again, this is an effort motivated by all the barriers that the black box paradigm is facing towards implementation of AI-ECG. And these characteristics of interpretable by design systems are excellent at addressing all these limitations. And the structured information that exists in 12SL and MUSE is arguably one of the best dictionaries for encoding human knowledge and reasoning that exists in the world. Again, this could be the perfect complement to black box models. It doesn't negate them. It actually tries to justify them and use them better than ever before and get the best of both worlds towards removing the barriers and actually realizing more widely the transformational potential of AI-ECG. Thank you.